All right, so now we're going to take a look at a different type of problem. This is one that begins dealing with some of our capacitors. Okay, so I've got a couple different questions that I've got here. I'm going to work through them. But we're starting off, and I'm going to say that I found a 2 microfarad capacitor. So I found a capacitor that has a total capacitance of 2 microfarad. As I mentioned, 1 farad is a very, very large amount of capacity. You can get 1 farad capacitors, they do exist, but it's not the sort of thing that you normally use in most electrical devices. You'll normally encounter things like microfarad, or maybe nanofarad, maybe millifarad, where it's the little m. In this case, we have microfarad. Okay, so I've got a 2 microfarad capacitor, and it has 10 microcoulomb applied to it. In other words, I've taken a bit of charge and applied it on there, 10 microcoulomb to be precise. Now that we're dealing with actual capacitors, we're probably going to deal with charges much more similar to this. I also mentioned when we studied charges that 1 coulomb is a whole lot of charge. And so when dealing with capacitors, especially on the order of micro, we end up with things that are on the micro or nano or sometimes milli. It depends on how much we've got them charged and how they're designed. Okay, well, we've got this capacitance. So this is capital C equals 2 microfarad. And our charge, Q, equals 10 microcoulomb. And I ask, what is the voltage across this capacitor? At least as my first question. Okay, well, in class we had the equation that our capacitance was equal to our charge divided by our voltage. Okay, so if I take this, I know my capacitance, I know my charge, and I want to find my voltage. So I'm going to multiply both sides by my voltage, so I can get it up in the numerator over here. And then I'm going to divide both sides by my capacitance to get my voltage by itself. After doing that, I end up with the equation that my voltage equals my charge divided by my capacitance. All right? Well, I know my charge, that's 10 microcoulomb. So that's 10 times 10 to the negative 6th coulombs. And it's going to be divided by my capacitance, which is 2 microfarad. Okay? Which is 2 times 10 to the negative 6th farads. Well, in this case, because they're both micro, our micros are times 10 to the negative 10, or negative 6th, will cancel out. And 10 over 2 is 5 over 1. That reduces down. We find that we have 5 coulomb per farad. And if you remember from class, I mentioned that the farad is equal to a coulomb squared over joule. Well, if I put that in over here, it's in the denominator. I end up with at least units. I've got coulomb divided by coulomb squared divided by joule. Well, one of my coulombs will cancel out, and this is in the denominator of the denominator, so I'm going to try and get it up into the numerator. So I'm going to multiply the top and bottom by joule over 1. These cancel out, and I end up with joule divided by coulomb, which, if you recall, is equal to a volt. So we do indeed end up with a voltage. A coulomb divided by a farad gives me a volt. So in the end, I find that the total charge, not the total charge, the voltage across that capacitor is equal to 5 volts. Okay? So the next thing that I ask in that particular question, same information, I ask, what is the energy stored in the capacitor? Okay, well, there are 2 ways to go about this. I gave you 2 different equations for our potential energy, our energy on a capacitor. It equals 1/2 our capacitance times our voltage squared. Okay, but I also mentioned, and I showed you the replacement in class, that this also equals 1/2 times our charge times our voltage. I could use either of those. I know my capacitance, I know my voltage, and I know my charge and my voltage. In this case, I'm going to use this one, mostly because then I don't have to square the result. I'm lazy like that. So my potential energy is 1/2. I'm going to use Q, our total charge. The charge on this was 10 microcoulomb. 10 microcoulomb times our voltage we found was 5 volts. Okay? Well, I've got 10 times 5, that'll give me 50, divided by 2. So this gives me, oops, I almost wrote 50. 25 microcoulomb times volt. Well, a volt was a joule per coulomb, so our coulombs will cancel out, and I end up with microjoules. Okay, so I have 25 times 10 to the -6th joules. So, in the end, I could phrase this as my potential energy equals 2.5 times 10 to the -5th joules to get my answer in SI. Although you could also just say 25 microjoules. Okay. The next thing I ask starts to get a little more confusing, or a little more complicated, I should say. Assume the capacitor is a parallel plate capacitor. We talked about those in class, in fact. I still have it out. So, we're going to assume it's this guy. This is a parallel plate capacitor. And we talked about the effects of a parallel plate capacitor. I gave you an equation for finding the capacitance on that guy. It was, our capacitance was equal to that crazy epsilon naught, also known as the permittivity of free space, which is the coolest name ever. And that's going to be times our area, the area of overlap. For the most part, it's just the area of the plate itself, just one of the plates, divided by the separation between them. Now, this isn't the complete equation. Technically, there's another variable that goes in here to deal with capacitors that don't have air or vacuum between the plates. For most of my classes, we'll only be dealing with air between the plates, so we'll just use epsilon naught. For APC, they have to deal with something called a dielectric constant, which tells us what happens when we put something that isn't air in there, and it will adjust the capacitance. But for most of my classes, this is the appropriate equation, and this one holds pretty well, at least for the ones that we'll be studying. Okay, I say that I take that capacitor that we were just playing with, the one that was a capacitance equal to 2 microfarad. And I don't give you any information about the physical dimensions, but I do tell you that I then take that separation and I cut it in two. I cut it in half. So let's say these guys start out this far away. I take them and I put them like this. They're now half as far away from each other. In other words, if I look at this way, I could say C1 equals epsilon naught times area 1 divided by D1. And then I went in and I changed things. So I end up with some C2 because I changed my separation. So I changed how much charge and energy I can store on that capacitor. I end up with epsilon naught. I didn't change my area, so that stays A1. But I did change my separation. I cut it in half. So I would write D2 here, but I know that D2 is equal to 1/2 of D1. Okay. Well, I've got 1/2 down in the denominator. I'm going to try and get that cleaned up a little bit. So I'm going to multiply by 2 over 1. That'll cancel that out. I have to do the same thing up here so I don't change my equation. And I end up with C2 equals epsilon naught area 1 divided by separation 1 times 2. We had a factor of 2 that came out of this. In other words, when I cut that separation distance in half, I got them that much closer together, I doubled the total amount of charge and energy that I can store in there. My capacitance doubled. Okay, so now I know what's happened to it. If I reduce the separation of the plates by half, what would be the voltage across the capacitor now? Okay, so I know that I doubled my capacitance. I started off C1 was equal to 2 microfarad. So what's C2 going to be? Well, while I don't know what the actual separation is, or the areas, I do know that I doubled it, right? I have a factor of 2 that showed up here. So I can hold twice as much, which means I go from 2 microfarad to twice as big. I'm now at 4 microfarad. Okay, well, I still have the same amount of charge on there. I just found this capacitor on a shelf, and I'm moving it around, but I'm not actually letting the charge run off. And so I still know that my charge, Q, equals, what was our charge? Our charge was 10 microcoulomb. Okay, so 10 microcoulomb. I want to know what my voltage is. So we found just a moment ago that our voltage is equal to our charge divided by our capacitance. Okay, and now I know that I've changed this out, so my charge is still 10 microcoulomb divided by, this time, 4 microfarad. Well, 10, again, my micros end up canceling out. They're both times 10 to the negative 6th. And so now I find that I've got 10 divided by 4, which is 2.5 volts. By doubling the capacitance, I actually cut the voltage across that in half. Okay. But now I know my voltage across it. I don't know how big the plates are. I don't even know what their actual separation is. But I do know how I changed it, and that's enough for me to find out what happens to my voltage across it. Okay, so the last thing that I ask, and I realize now after looking at it, what I meant to ask was, what should I do to the diameter of the plates? But instead I actually asked, okay, now that I've put them twice as close together, what do I need to do to the area of these guys to actually make it go back to the original voltage it was at? I want to undo what I did before. I want to change that capacitance. I had C1, which was equal to 2 microfarad. I turned it into C2, which equaled 4 microfarad by shortening the distance, the separation between the two. And now I want to find out what I need to do to the area, C3, to bring my capacitance back down to 2 microfarad. Okay. Well, I know that to go from C2 to C3, let's take a look. I need to, what do I need to do to my capacitance? I need to cut it in half, right? So I plug these back in, I'd have 4 microfarad here. I'd end up with 2 microfarad there. 4 times 1/2 would give me 2. So if I can cut my capacitance back in half, remember the first time I doubled it, now I want to cut it in half. So what do I need to do? I know that C2 equals epsilon naught area. In fact, let me drop off the 2. We're just talking about the capacity in general. Divided by our separation. Well, free space isn't changing. The permittivity of free space isn't changing. I've set it up where I want to keep that new separation where they're closer together, but I want to change the shape of the capacitor so that I get back my original capacitance. I need this to become half of what it is. Well, epsilon naught isn't going to change. Our separation isn't going to change. So what do I need to do to my area to make this still equal? Well, I'm going to need to multiply it by half, right? Because then I'd have a half there, I'd have a half. I could also redraw this. I don't want to do this. 1/2 equals 1/2 multiplied by epsilon naught times A. Sorry, I guess I don't need a parentheses there anymore. Well, that works, and the halves would cancel out, and I'd get my original capacitance back. So what I need to do is, I need to cut my area in half. In other words, A3 equals 1/2 of whatever my area was at point 2, right after I put them close together. Okay, So that's a little bit of applying the new equations that we have for a capacitor to find out the voltages across them, the charge that they have on them, or we could solve for that, but that's not one of the things that we actually did. We found the energy stored in it, and then we started playing around with the physical dimensions of the capacitor to see how that affected some of the values that we had.